last time we mentioned that after covering chapters 3, 4, and 5, we're now capable of analyzing both signals and systems in both the time and frequency domain. Okay. Now in chapter 6, we sort of review some of the time and frequency characterization of different signals and systems. Okay. So one of the main motivations for studying this time and frequency characterization is in the study of filters, okay, or in particular frequency selective filters. Okay. So through the study of this time frequency characterization, we can understand some trade-offs that we may encounter when designing these frequency selective filters. So for example, suppose you start out with this ideal low-pass filter with the frequency response that looks something like this. Okay. So if you look at this frequency response, it basically lets through signals perfectly. It lets through signals perfectly lying between minus omega c to omega c and completely eliminate signal outside of this frequency band. Okay. Now this is the corresponding discrete time version of this low-pass ideal low-pass filter. Now for such a perfect low-pass filter in the frequency domain, in the time domain, you get an impulse response like this. Okay. So even though this looks so perfect in the frequency domain, in the time domain you actually experience all these large ripples that decays actually slowly over time, and this may cause certain problems in practical applications. Okay. But one thing you can observe here is that when you look at this filter, right, which has a bandwidth that is proportional to this omega c, its impulse response will have a pulse width that is actually inverse proportional to omega c. Okay. So suppose you have an ideal low-pass filter that has a bandwidth that is proportional to omega c. Okay. Then the pulse width in the time domain will be proportional to 1 over omega c. Okay. So by this relationship, you observe this trade-off that we have seen in many previous examples, where a signal with a larger bandwidth, right, or a system allowing through larger bandwidth, will have an impulse response or time domain signal that has a smaller pulse width, okay, and vice versa, right? Now, if you look at the step response, right, if you look at the step response, which is just the integral of the impulse response, you get something like this, okay? And this shows you several, non-ideal properties in the time domain, right? So first of all, compared to an ideal step function, that would be 0 in the negative axis, jumps up to 1, and then stays perfectly at 1 afterwards, right? Compared to this ideal unit step function, the step response here, right, takes some time, right? Takes some time to go from 0 up to 1, right? So this implies that we would need a non-zero rise time. Okay, so this implies that we have a non-zero rise time. Okay? And that this rise time is proportional to 1 over omega c. Okay? So the larger the bandwidth, the faster you are able to rise from 0 to 1. Okay? And vice versa, if you have a smaller bandwidth, then it would take you a longer time to achieve this rise. Okay? And secondly, you observe an overshoot. Okay? So, you observe this rise sort of overshoots beyond the unit gain that we hope to achieve, and that afterwards there is some oscillating behavior before it gradually settles down to the desired gain. Okay? So all of these things may cause some undesired property in practical applications. Okay. Right? And this oscillatory behavior is also sometimes called ringing. Okay. So this is telling us that there is some trade-off, right, between the frequency domain and the time domain characteristics. Right? If you want a perfect frequency response, right, you need to live with these non-ideal properties in the time domain. Okay. Now, like I mentioned last week, right, this ideal low-pass filter is not really implementable in practice. Okay, you can never actually implement something so perfect using practical circuits. But even if it is practical, right, even if you can implement this, you may still not want to, because of these non-ideal properties in the time domain. Okay? So depending on your application, you may want to provide some flexibility in the design. Okay? So instead of having such a perfect frequency response, sometimes you can live with a little bit of flexibility or tolerance in both the pass band, stop band, and in the transition time. Okay, so in particular, instead of requiring the pass band to have a perfect unity gain, sometimes you can tolerate a delta 1 discrepancy from the unity gain that you desire. Okay. Okay. And in the pass band, right, instead of requiring it to be perfectly 0 in the stop band, sometimes, right, you can provide a delta 2, a certain small amount of flexibility, okay, in the stop band. And you can also allow the transition from pass band to stop band to occur within a non-zero transition band. All right? okay? Now, allowing for some tolerance in these different factors often helps you obtain, slightly better characteristics in the time domain, okay? So with some tolerance here, you can often obtain a time domain signal that has a faster rise time, or maybe a smaller overshoot, or with a faster, or a faster settling time, right? You can have a shorter time before the signal actually settles down to unity. Okay. Now, sometimes your design is specified in terms of the desired time domain signal rather than the desired frequency domain signal. Now, if you want to do that, then you can specify these values that I just mentioned, right? For example, the rise time TR, which is the time it takes to get to the unity gain that we want, right? This overshoot value delta, or this tolerance of delta. Okay, this is capital delta. This tolerance of lowercase delta, right? That you can live with, after it settles down. Okay. Right. So these are different variables that you may be, concerned with, right? Such as the rise time. This is the overshoot value. This is the settling time. Okay. So the settling time is the time it takes, okay, for this oscillating behavior to, settle down to within delta of the unity gain. Okay. And so sometimes you're also concerned with this omega r, which is the oscillating frequency. Okay. Right. Okay. So in designing, in designing this frequency selective filters, you often need to, trade off between properties in the frequency domain and properties in the time domain. Right? Sometimes, a more ideal frequency response may lead to less ideal time response, and vice versa. Okay. We have an example. Okay. So here we have, two implementations of the low-pass filter. One is called the Butterworth filter. The other is called the elliptic filter. Okay. So here on the left-hand side, you have the frequency response. The dashed curve is the Butterworth filter. The solid curve is the elliptic filter. So you can see here that, the elliptic filter has a much shorter transition band, right? So this looks more ideal, right? Closer to the ideal low-pass filter, whereas the Butterworth filter requires a larger transition band. Okay. So the transition band is smaller for the elliptic filter. Okay. But then what is the consequence of that? Right? If you look at the time domain step response, you see that the elliptic filter, right, overshoots much higher than the Butterworth filter, and that it oscillates, the oscillatory behavior is also more significant. Okay, so it settles down much slower than that of the Butterworth filter. So the overshoot and the oscillatory behavior, which we also called ringing, are more serious than the other. Okay? All right, so this is just an example to let you see that there, if you want a more ideal frequency response, you often have to live with a less ideal time response, and the other way, similarly, the other way around. Okay. All right. Now, another topic we talked about repeatedly in previous chapters are systems that can be described by linear constant coefficient differential equations. Okay? Now let's see how this kind of system characterizes in the time and frequency domain. Okay. So suppose we start out with this first order system. Okay. That can be described by this first order differential equation here. All right. Now here we have tau times the derivative of y plus y equal to the input x of t, and tau here is a certain time constant. Right. Now if you take the Fourier transform on both sides, right, move x to this side and all the other coefficients to the other side, you can obtain the frequency response that looks like this. Okay, and the inverse Fourier transform of this is this single-sided decaying exponential that we derived several times already. Okay. Now you can see that this tau, this time constant tau, sort of affects how fast the impulse response decays over time. Right? If you choose tau that is smaller, right, this decays much faster, meaning that the system responds faster. Whereas if tau is larger, this decays much slower. Okay? Now you can also observe this in the step response. The step response is just the integral of the impulse response. All right, you can see that if tau is smaller, then the rise time is shorter. Whereas if tau is larger, the rise time is slower. Okay? But then how does this affect the frequency domain? Right? So if you have a larger tau here, okay, if you have a larger tau here, then this corresponds to a smaller omega. Okay? All right. Okay, so you can see here that tau is, divided, t is divided by tau here, whereas omega is multiplied by tau here. So the dependency, the relationship of the time on tau is opposite from the dependency of omega on tau. Okay? Right. So this time constant here controls the rate at which the system responds. Okay. Now let's look more carefully at this frequency response here. So as we mentioned last time, right, when we look at the frequency response, or if we want to visualize it on a figure, we often want to plot out the Bode plot. So the Bode plot is the plot of the magnitude and the plot of the phase. Okay? So when we plot the magnitude, we want to look at this 20 log of the magnitude of the frequency response. Okay? Now, if you look at this, the magnitude is one over omega tau squared plus 1. Okay? So if you take 20 log 10 of this, right, the square root brings a 1/2 outside. 1 over this brings a minus 1 outside. So you get a minus 20 times 1/2, which is 10, of log 10 of the denominator here. Okay? So this is the log magnitude that you get in the Bode plot. Right. Now, instead of looking at the exact values at every point of omega, right, sometimes we can just look at some extreme values to gain some understanding of the trend of this response. Okay? Now, if you look at this, suppose that omega tau is much less than 1, right? Suppose that omega tau is much less than 1, or that omega is much less than 1 over tau, right? Basically, if omega is small, then 1 dominates this term, and log of 1 is just 0, okay? So when at low frequency, the magnitude is actually approximately 0, right? Now, when omega tau is much greater than 1, or in other words, if omega is much greater than 1 over tau at high frequency, then this term dominates, okay? So we can, neglect this 1. So I can bring a 2 outside, which gives me minus 20 log omega tau, or I can split this into 2 terms, minus 20 log 10 omega minus 20 log 10 tau, okay? So tau is just a constant. Tau is just a constant, so what really scales with the frequency is this term here, okay? So if you plot it on the figure, what this gives us, is a line at the low frequency that is equal to a constant 0 dB, right? A constant 0 dB. And at high frequency, we have a straight line, with respect to, because this x-axis is plotted, in log scale with respect to omega. So in the x-axis, right, we have this log omega, which decays at a slope of minus 20. Okay? So at low frequency, it can be approximated by this 0 dB line. And at high frequency, we approximate this by this line that decays by 20 dB for every increment of log omega, okay? So when do you increase log 10 omega by 1? Right? It is when omega is multiplied by 10 times, okay? So every time omega increases by 10 times, log 10 of omega increases by 1, okay? So a 10-fold increase is called a decade, okay? So this means that the gain will decrease by 20 dB every decade, okay? So this is called the minus 20 dB, or the 20 dB per decade, okay, asymptote. Okay. So even without, calculating out the specific values of this log magnitude, we can already obtain the approximate behavior of this frequency response by just looking at these two lines here. Okay? And these two lines are actually the low frequency and the high frequency asymptote of this function here. Okay? This is the low and high frequency asymptotes. Okay. And the point for which these two lines intersect with each other, right, is called the break frequency. Okay? And you can see that, the intersection of these two lines is exactly when omega is equal to 1 over tau. Okay? So if omega is equal to 1 over tau, right, then this term becomes, equal to this term, right? So they cancel out to become 0 dB. Okay? So the intersection occurs at omega equal to 1 over tau, which we call the break frequency. Right. Now the big, right. This is tau 分之一 对。OK。OK， 谢谢。还有没有其他问题？ Okay, so we're using these two asymptotes to study the approximate behavior of the frequency response, right? Now this fits pretty well with the actual frequency response. The biggest discrepancy lies at the break point, break frequency here, okay? The largest discrepancy occurs here. Now, if you plug omega equal to 1 over tau inside here, right, you will get minus 10 log 10 of 2, right? This is 1 plus 1, which is 2. And minus 10 log 10, 2 is exactly, minus 3 dB, okay? So the largest discrepancy between the approximate curve and the actual frequency response is 3 dB, and this occurs at the break frequency. Okay. Right. So this is probably another advantage of plotting the log magnitude rather than the actual magnitude, because in log scale we can actually obtain this simple approximation of the frequency response. Okay, and this allows us to gain some insight about the behavior of the response without actually calculating the specific values at each omega. okay, which may require, some computer software or calculator, right? Now you can do the same thing for the phase as well. You can try to approximate the phase with these simple straight line functions. Okay, so in this case, the phase is minus arctangent omega tau. All right, so you can compute this from the original frequency response here. Okay, so the phase is minus arctangent omega tau. Now, when omega tau is very small, close to 0, arctangent is also 0. Okay, so for omega tau very small, let's say less than 0.1. So for omega tau less than 0.1, which means that omega is less than 0.1 over tau, we can approximate the phase as 0. Now, when omega tau is very large, then arctangent of a very large value is close to pi over 2. So minus that gives you minus pi over 2. Right? So suppose that I consider omega tau greater than 10 as large. So I approximate this, right, for omega tau that is greater or equal to 10. I approximate it by the phase minus pi over 2, right? Or in other words, we approximate the phase like this for omega greater or equal to 10 over tau, okay? And then in between, we can just draw a straight line, right? So this straight line is obtained by just connecting these 2 points, right? So for omega less than 0.1 over tau, the phase is 0. Beyond 10 over tau, it's minus pi over 2. And then we just use a straight line to fill up this remaining part. Okay? Right. So this is a linear approximation of the phase. Okay. And you can see that the actual phase and the approximate phase actually intersects at this point here, which corresponds to the break frequency. So this is, the Bode plot, or the approximation of the Bode plot that we can get for a first order, for a system that can be described by a first order linear constant coefficient differential equation. So we can do something similar for, second order systems as well.